Okay, hello everybody, and I think we can start the third lecture. In this lecture, we try to start from where we left off last time. We actually didn't finish the DFT, and just we can say that the Z transform is almost explained completely. But without the examples, you can just go through the books, and you can find several examples from each of these transforms. You can practice it, and here we try to explain more about the DFT today, and the rest of the things that, the peripheral ideas that comes after DFT, and also some details about the sampling, and some other techniques like the downsampling and upsampling, which are really useful when you want to deal with the filter banks and polyphase filters and so on. So just recalling from the last time, we saw that discrete time Fourier transform is a transform, or is a kind of analysis of the signal, which gives us the information about the frequency components inside a signal. But there was a big problem with DTFT, and the problem was that the frequency representation of the signal is continuous in frequency domain. So it means that if we are intended to do any kind of processing over the frequency samples or the frequency, the frequency components, it's not possible to have it inside the computer. So the x of e to the power of j omega is a continuous, actually here we see that the signal, the time domain, has a continuous relation with the omega, the frequency domain. So that makes the problem a bit difficult. That was the idea or the intuition behind the DFT transform and how it was devised. So this slide, I also chose this slide from the previous lecture because I thought that the idea behind these slides that I bring up from the previous lectures in some other future lectures may help us. So that's why I just repeated these slides. So from this slide we understood that the stability of the system is equivalent to the continuity of the frequency response. And we understood that's impossible to have an ideal low-pass filter implemented in practice. So we went through some very general the sequences and the corresponding Fourier transforms. The Parseval theorem is something very useful. I repeated it here just to remind us in some future lectures. And some of the pairs, the DFT examples. And we can take a look at the second row and the 10th row, and it gives us a kind of lemma, which is called the duality lemma. It's very important. So you see that the delta shifted by n0 value samples in the Fourier transforms is corresponding to the exponential with a negative phase. And here you see that if we have an exponential, so here is a positive phase, but we can just simply replace it with a negative phase, gives us a series of the delta which are repeated by 2 pi k. These two rows actually gives us a lemma, which we can use it later. We'll see it. As an example, we went through the ideal window, just as a window from -n to n. we have 2n plus 1 samples. The amplitude of the samples is considered to be 1. So we consider it as an ideal window, and it's normal. It's just like a window. From minus n to n, and for the 0. So entirely we have just we have 2n plus 1 samples. This is called the window. And we saw that the DTFT variance of the window, or the frequency response of such a window, gives us a sinc function. The frequency response is a sinc function. Now if you go to the duality, you'll understand that. So the window in the time domain gives us the frequency, in the frequency domain gives us a sinc function. So if the sinc function is in the frequency domain, what should be the corresponding, if the sinc function is in the time domain, so this from the time, if this is the time domain signal, this gives us a sinc function. In the frequency domain. Now, if such a thing is in the time domain, if this is in the time domain, I'm not setting up the values, it's just the general picture. I'm just portraying, the duality lemma in general. I'm not talking about the values, what's exactly here or here. This is just the general idea. So this was for the frequency domain. Now if this is the time domain, what should be the one that we get in the frequency domain? If this is in the time domain, you will have something like the window in the frequency domain. That's why I told you to look at the second row and the 10th row. That gives us something. That's the kind of idea. But we can also take a look at the book, and maybe I can bring it up in one of these exercises. The one, maybe today actually we'll release it. And by the way, the first exercise is released already, so you can take it and can start working on it. The second exercise, I think we'll try to put it in the website maybe by tomorrow or the day after. But the deadlines will be the same, and so it will be next coming Monday. And the tutorial session, probably the first tutorial session will be because I'll take one of the first tutorial sessions from both groups. I will take it for the course. And the second one onward, you'll have actually the tutorials. So that was the example. Just I wanted to bring this example because there are a lot of ideas coming afterwards. So if we have a window in the time domain, we will get something like a sinc function in the frequency domain, and vice versa. But I'm not talking about how to set the values, just the general big picture of that. So the idea of the DFT came from this problem that the DTFT had about the continuity of the function over the frequency domain. So in general, in analog sampling, we saw that if signal is limited in the bandwidths in the frequency spectrum, so if the signal that we have doesn't start, it's not with the infinite number of the frequency components. The frequency components will end at some point. Then we can have a kind of, so if we can do the sampling in such a way that it's lossless, so the signal itself can be resynthesizable without any errors. So we have the lossless representation of signal by samples, and it's possible. In the same way, because in DFT, what we are trying to do is we are somehow trying to take samples from the DTFT version of the signal. So we have the signal x e to the power of j omega, which is the DTFT, continuous in frequency. We want to take some samples of this, which are good representation of the signal. So if we take these samples from x e to the power of j omega, which is DTFT, if we take those samples and we keep it inside the computer and we do the processing, or even we do nothing, just we want to resynthesize it again, we can get this exact signal in the end. So we need to do another kind of sampling, but this kind of sampling is done in the frequency domain, is actually over a signal which is a function over the frequency. So here also we have a kind of sampling. So with DFT domain sampling, then the same criteria should be applied. So the signal should be limited in the time domain. This time it should be in the time domain. Then we are able to have a lossless representation of the signal in the frequency domain by its DTFT samples taken from the DTFT. So we have an aperiodic signal in time domain, x of n, and we got a continuous in the frequency, x e to the power of j omega. Now we want to take samples from this to keep it inside the computer. We want to study what happens over the samples in the frequency domain. Because this x to the power of e j omega is periodic, we saw that x of n is aperiodic, but when we go to the frequency domain and we take the DTFT, it's a periodic signal. Because it's periodic with a period of 2 pi, so we can say that we take n samples. We're not talking about what n should be. We're just talking about a specified value of sampling rate, which is n. N number of the samples, if we take, so then probably we should be able to reconstruct the signal completely without losing any kind of information. That means the DFT samples are DTFT samples taken every k 2 pi over n. So if we divide the frequency bandwidth into n divisions, and here we consider the equidistant divisions, and we take every sample using k from 0 to n minus 1, then we should probably have the samples of DFT. But what kind of, what should be this n to be able to have a proper x of k which keeps the entire information which was already inside this representation? That's the story of DFT. So the big difference between DFT and other, the previous representations is that we have a new parameter defined, and that's n. That's a new parameter that we should have it. In the previous examples, we had just the signal, and based on the signal, what's the representation in the frequency domain? Now we have the signal, but still we have to say how many samples we want to take from the DTFT version of the signal to get the DFT values. That's why if you go to the computer, for example, writing the MATLAB codes, you say take the FFT as an algorithm that implements the DFT. You should write down, take the FFT with n number of the samples, and n is a parameter that the user should give to the function. So I brought this example, this graphical example, to be more illustrative about what we're trying to do actually. DFT and DFS, or discrete Fourier series, probably have already practiced this in previous lessons that you had, signal theory or whatever. They're correlated. So what is the relation between discrete Fourier series and discrete Fourier transform is denoted here in this picture. So in general, we say that we know that for the DFS, we had a periodic signal. We had a periodic signal. Every periodic signal we can demonstrate it with x tilde. Now, so here we have a periodic signal with period n. So we see that this sample in 0 is repeated in the n location. For DFS, discrete Fourier series, we have actually this representation in the frequency. So every periodic signal is capable of being demonstrated using the harmonic signals, but the values that you give to the harmonics, the first harmony, the second harmony, and so on and so forth. So these are the values that you should give to those harmonics. Now, the relation between DFT and DFS is that you just take the x of n. I said that the samples in the time domain should be limited. So we have just the main period of the signal of x tilde of n, and we got only the first period of the representations in the frequency domain as the samples of DFT. So that's the intuition, but how it comes in mathematics is here. So in DFS, if you have a signal which is periodic and you want to get the corresponding coefficients in the DFS domain, in Fourier series domain, you have actually this W of n is already defined here, is e to the power of minus j2 pi over n, which is one of the basis functions in the frequency domain. So it's just the values of this, the inner product or the similarity of the signal, which is periodic, with these basis functions. And now the corresponding DFT values are exactly these values, which are only taken from a window of 0 to n minus 1. So the main window of DFS. And we intuitively, when we're talking about that, we mean that anywhere else it should be 0. And for the synthesizing of the periodic signal, we have just the equivalent with the conjugate basis, and here is also the same. But we have the signal normally in the time domain. What we need is in the frequency domain. So, if you write down the analysis and the synthesis form of the DFT values, it comes like this. For the analysis and for the synthesis, we have these bases which are conjugate with respect to each other. So this kind of transform, we are also able to demonstrate these transforms as a matrix operation. So when you want to implement it probably in MATLAB or in C code, the matrix form would be much easier, I think. So you have the signals, the DFT values of the signals for the main windows, 0 to n minus 1. So if we have already considered that we want to take the endpoint FFT or DFT, so the endpoint DFT means x of 0 to x n minus 1, and this is the transformation matrix, which is predefined. Just if you know n value, we can put it inside this e to the power of minus j n 2 pi over k. And these are the samples in the time and we can get the values of the DFT, and this is the inverse DFT. So it can be represented in the matrix domain very easily using the MATLAB codes, and this is the closed form representation of it. But as an example, consider that we have x of n like this. So the top graphic is the x of n that has only values for from 0 to 4. 5 samples. And assume that all the values are 1. So when we say n should be 5, we take n to be 5. It means that what we're trying to do is making this x of n periodic with a period of 5. So it will look like this, as if all the samples are 1. From minus infinity to plus infinity, everything is 1. And if you go through the series expansion for the DFS, you see that such a thing will give you this equation in the end. And you see that the values are for 5 times the 0, and the multiplications of 5 will get the value of 5, but anywhere else it's 0. But if you just take the first period of that, so from 0 to 4, the only active value is in 0, and that's 5. So the signal which was in time domain as if like the xn, in the frequency domain based on DFT is represented like this, just with one sample. If n is equal to 5. If n is equal to 5, that's the only value which is valid. This implicitly tells us that many times signals in the time domain can be represented much sparser in the frequency domain, in the DFT domain. What does it mean by representing a signal with the sparse components? It means that the less components of the signal is active in DFT domain than in the time domain. In the time domain, you have 5 samples active, but here in the DFT domain, you have just 1 sample active. This is the idea behind the sparsity, actually. Many of the sparse-based algorithms, they use this. For example, in a speech case, that's a kind of fact, that we know that the speech signal in the frequency domain, when you take the FFT of the signal, is much, much sparser than the signal in the time domain. And we use this fact in many algorithms. So, the next example is when we take n to be equal to 10. So in the previous example, n was equal to 5, and now it's equal to 10. And what happens? You just make the signal periodic with the period of 10. You continue from both sides. And then you take the DFS value, but you will keep the DFS values just for the first period. And this is the new values that you will get it. This is for the magnitude and this is for the phase. We just care about the magnitude at the moment. So here you see that if you use n equal to 10, then the values are different. They're quite different. So it's very dependent on what should be the value of n when you're using the DFT. Other properties of DFT, besides the linearity and the duality, so for the linearity is the same as many other transforms. That actually all the transforms that we talked so far, they're all linear. So the linearity property is already satisfied. But here is a very nice example of shifting. So shifting in the DFT domain is a bit different from the other domains. So when we do the shifting here, because we have a confined period, a concentrated period, the first period, which is n samples, when you do the shifting, you're actually doing the circular shifting. So the values are circulated inside that period. Here is an example of x of n when this is made periodic with a period of n, so we have the x tilde of n. And now if you shift this, n plus 2, so you're doing the left shifting, what has happened here is that you're actually lefting to the left side. So the left side shifting, you see that the values go to the left, so this value is coming here, and for the next 3 values they're coming afterwards. But these 2 values are circulated and coming from the other side, they come into the window. So that's called a circular shifting. So in DFT what we have is a circular shift, and it's not a normal shift. And how it's represented is here. Because everything should happen inside a window with the n samples. So that's why always in the shifting we have something like this. We write down, for example, x of n shifted by m values, but they are all inside a period or a window with the n samples. But the corresponding value should be like this. So if x of n gives you x of k, then this kind of shifting or circular shifting gives you this kind of value. So these properties you can easily find it and follow it in the books. I'm not going through that, but maybe you can follow them in the exercises. So what's remained from the sampling, which is really important, I'm going to bring it here, which ends up with the down and up sampling and changing the sampling rates without taking the analog signal sampling again. So that's very important. We know from the previous lecture that we have the continuous time signal and we use the continuous to discrete converter. In this block we need actually the sampling period or the frequency, which is reverse of that. And we got the sampled values x of n. Then we use the quantizer with the values we already know how to set it, and digitizing in the bits. How it's represented graphically is here. You have the continuous time signal. If you take those samples, you'll probably have something like this. But what is practice, I mean in practice what you have is a zero order hold. So based on every of these samples, because it's not possible to have this single sample in the electronics. So what you practically have is this zero order hold, which you have the samples, you keep it for a while and then continue with the next one. So it will look like this, but here the values that you have, the amplitudes, not necessarily they are quantized. So you have the quantization values here. So the next step is the quantizer, which it means that you have to truncate the values and round it with something which is already quantized. So that's the final result of quantization of the signal. But what is the relation between the sampled version and the continuous version of the signal in the frequency domain? So what is the relation between the frequency representation of these two? Is that completely the same or there's a difference? This is actually one of your exercises, which we consider it as a bonus point, but we actually asked you to bring up the first approach based on the hints that we put inside the exercise, but this is the second approach. But at least you can check your result finally to get something quite similar for this one, which here is just a partial solution from the second approach of the same exercise. So that's also a bonus for those students who participate in the class, sometimes they get some, the solution of the exercises, but maybe another approach. So, what we have after doing the analog to digital converter is x of n, which in the frequency domain is represented by dTft. If you write it down based on the definition of the series, so what you have is like this. But we already know that x of n is the sample version, so it's actually is x and t. But we implicitly removed t from all the equations. Now we can bring it back here. If we do that, what we can do here is x and t, we can represent it based on the analog version of, so the discrete continuous time Fourier series. So it's in time, so we can bring it in the time domain representation, which is actually integral over minus infinity to plus infinity, x of the continuous version of the signal. Instead of t, we are putting nt here. It's in the time domain. But here, we are able to replace the sigma and the integral. Why? Is that something that we can generalize it always to replace the sigma and integral if they are coming one after another? Or do we need a kind of condition? First of all, if there is an integral or the sigma which is limited from both sides, then definitely it's not something to diverge. So if you have something, for example, from minus infinity to plus infinity, and here you have something which is limited from both sides, definitely you can replace it without any problem. But if this is not the other way around, or something like this, if both of them are from minus infinity to plus infinity, you can replace them if they are both limited. So based on the biboy stability, if they are absolutely summable, then you can replace it. And both of these operations, the sigma and integral, they are both linear, so you can easily replace the linear transforms if you have the biboy stability, or here the absolutely summable property. You can easily replace them. We already know from the definition that they should be, and they are, so we can easily replace them. Replace the integral and the sigma. But we know that this value has nothing to do with omega. So, yeah, we can actually take it out of this sigma, which is, has nothing to do with n. So we can take it out of this sigma, which is just dependent on n. We'll bring it out of this, and we just keep the other exponential value, which is dependent on n. And then we merge it with the previous exponential value. Now it's a place to use those lemmas that I told you, actually, the duality lemma, looking at the second row and the 10th row of the second slide, using the lemma which is called the Poisson's formula, and replacing this omega with omega plus 2 pi k over t, or the other way, you can say omega t is equal to this value. Then it's just a definition of, so in general, you'll just come up to this formula in the end. So I skipped through the solution, this part, But if you just look after the Poisson's formula, it's just a piece of cake from here to here. But what it gives us is, look at the DTFT of the signal and the CTFT of the input signal, how they are related. So x of g, e to the power of j omega and xc, which is continuous. The relation is that whatever xc you have, the amplitude is attenuated by 1 over t. So if you have, for example, it's like the spectrum of the analog input signal. If the spectrum of the signal, which we know it should be band limited, is something like this, as an example, which is bounded between omega n and minus omega n with the value of 1, then what you'll see here in the end, you'll have the amplitudes 1 over t, but it's repeated, the k values, it's repeated like this with 2 pi values. So here if it's 0, then the repetition is from 2 pi and minus 2 pi, and from both sides, left and right hand side, you can repeat it. And the relation between the previous omega and the new omega, if you just put k equal to 0, you see that every omega of this domain is just omega t. So omega n, new omega in this domain, in the DTFT domain, is omega nt. So this is how these two graphs from CTFT and DTFT of the signal after doing the A to D are related to each other. Now the question arises that what should be the requirement if we want to be able to recover the signal completely? In order to recover the signal, we need to put a filter here in such a way that the base spectrum, the baseband spectrum, this one, has no change. If we can make it, then we can recover the signal completely. So the signal should be band limited. So the signal should end at omega n minus omega n somewhere. And that's important, that when we want to recover the signal, we need such a thing, such a filter. And this filter in frequency domain is like an ideal filter, ideal low-pass filter. And we saw already that in the time domain, if we have this, we have sink in the frequency domain. Now, if we have such a thing in the frequency domain, what should be in the time domain? So it means that in the time domain, we will face with something similar to sink function. So sink functions are also basis functions in the time domain. And you can just study over the sink functions that they are also orthogonal, just the same as the e to the power of j omega n, which are orthogonal to each other. They are also the same. So the bases are, these are also the bases that you can construct a signal with. So what we're trying to do is to make a conclusion over the sampling rate, which is also one of the exercises, but I think a part of the exercise. What we saw here, so this is actually from your exercise, that you have the continuous time signal. It's a mathematical representation of sampling that is just like to have an impulse train, the train of impulses with a period of t, multiplied by the signal. I'm telling about multiplication in time, which in frequency domain is convolution. So you have the signal, the pulse train, and then you need something that converts the pulse train to the samples. What happened, as we had in the previous slide, was that we had xc j omega, which is a band limited signal, what happened in the frequency domain, we had a repetition of that with the value of the amplitude changed, actually attenuated 1 over t, and repeated by 2 pi. Here the omega s, which is the frequency of sampling before doing the structure, is 2 pi over t. So here is the omega s. So 0, omega s, minus omega s, and so on. If we want to be able to reconstruct the signal completely, then necessary condition for that is not, because here we have a repetition, or here we have a repetition. The necessity is that these consecutive spectrums of the main signal in the baseband and the repetitions from the adjacent bands do not overlap on each other. So for example, here we have omega s, and based on the bandwidth of the signal, if here is omega s, which is 2 pi over t, so here should be omega s minus omega n. So the necessity or the condition is that omega s minus omega n, which is this point, should be bigger than omega n, such that we have a kind of guard band here. We call this as a guard band. We have to make this guard band for the sampling if we want to be able to recover the signal. So omega s minus omega n is bigger than omega n, which means that omega s should be bigger than 2 times omega n, at least. That's the necessity, at least. This 2 omega n, or if we use based on the frequency f as a hertz, we say that f of s, frequency of sampling, should be at least 2 times bigger than f of signal, the maximum frequency of the signal. This is called the Nyquist rate. So that's the requirement of sampling if you want to get the signal back without any changes, without being corrupted. That's called the Nyquist rate. Any questions so far? So based on the idea that I told you, when we have repetition of the band, repetition of the spectrum with the period of 2 pi, when we want to recover the signal back, we need to take the baseband one, the spectrum, the baseband, and to do the inverse filtering. But how it's possible? So we say that if we do no processing, there's not kind of any kind of processing, just we take the sampled version of the signal and we want to recover it back to the time domain. But what we need as a condition is that the signal to be intact. I mean, the resulting analog signal should be completely the same as the input analog signal. So that's the necessity, that we need to use a kind of a structure or filter here that gives me the reconstructed version of the XR, T, which is quite similar to the analog input signal. If we go to the frequency domain, it means that, because here always when we have a system and you have inputs and outputs, the output has a convolutional relation with the input in the filter, which in the frequency domain, we assume that both, here for example, we have the time domain of the signal, and here, if we assume that is MT, then we can write down everything based on the CTFT. And the CTFT says that x of r, j omega, has this relation based on the frequency representation of this and this. So, based on the ideal low-pass filter that we already showed in the previous, the 2 slides before, this filter should perform like this. For the values of the omega in the baseband, it should have the gain of t to compensate the 1 over t. So the t and 1 over t, they compensate each other, and the final gain value would be 1. And that should perform for a certain bandwidth. What's the requirement for this bandwidth? The requirement is that this cutoff frequency, we call this as a cutoff frequency. The cutoff frequency of this filter should be between omega n and omega s minus omega n. So inside the guard band, we had a guard band, and this filter should fit into the guard band. So that's the requirement of this reconstruction filter. That's the reconstruction filter. But based on the duality, if we have something like this in the frequency domain, so such a thing in the frequency domain gives us a sinc function in the time domain. So the corresponding value, the corresponding representation of this ideal filter in the frequency domain is this filter in the time domain. It's just to say that the value of xn should be convolved with this time domain filter to be able to reconstruct the signal without any changes. And the same representation in mathematics is just the sign. For example, this is called, if you want to write it down as the sinc of t, the sinc of t is the sinusoid over pt over pt. But here we have pt over t. So what's the reconstructed signal? Based on the previous slide, so the reconstruction happens using this ideal filter with the samples of the dt of t, which was the sinc function. And in general, it means that if here when we see the series, it always reminds us the inner product. So it means that samples of x of n, those samples are the coefficients for the sinc functions which are shifted. So the sinc functions which are scaled with x of n and shifted, they can reconstruct the signal back again in the honorary signal. So it's just like that. We have the xn values. You have the sinc function like this, which in the origin is just 1, and every t period, t to 2t, and so on, is just 0. And you have this combination of the sinc functions. These sinc functions from minus infinity to plus infinity. So it's somehow like interpolating upon the xn samples using the sinc function as basis. So it brings us some problems. One of them is very intuitive, and we saw that that series, that summation, goes from minus infinity to plus infinity. So if you have xn samples and you want to reconstruct the signal back, you need a summation, actually infinite number of the summation, and that's the problem. In practice, you cannot do that. So what does it mean? It means that the reconstruction is not possible. You have to truncate the sinc function from some parts onward. It's not possible to have the sinc function, the infinite amount of the sinc function. So that sigma over n should be truncated in a place, in a very specified n. It should be truncated. But that n should be in such a way that it makes a less hurt to the final reconstruction. So we should truncate this sinc function which is shifted, and it's scaled by the values of x of n. There's no doubt about it. So it's the first problem. And it comes from this idea that ideal low-pass filter is not possible because we have no ideal low-pass filter. That's the reason. The second problem is that if you have a signal with the bandwidth which is higher than P over T, so omega of sampling, what happens? If the frequency of the sampling that you can make is less than the maximum bandwidth of the signal that you have. So, denoting in the picture, you will face with such a thing. A signal with the bandwidth, the spectrum of the signal, having a bandwidth higher than the sampling rate. So, we should study that. If we have just a continuous to discrete and then a discrete to continuous, or if we put a filter in the beginning, a low-pass filter in the beginning that cuts the signal from somewhere to somewhere. For example, cutting the signal in the window that we are able to have the filter, and then doing the rest of the thing completely the same. Which one gives us the final end, which is much closer to the analog signal after doing the reconstruction? The answer is the second. Intuitively talking about the idea, you can just, based on this, so this is the error. You have XC as an input, and you have one of these X1 or X2 in the output. So which one gives the minimum of error over the entire those sigmas? Which one gives the minimum of the error? It's energy of the error, actually. Here we have the square. So it's the energy of the error. Which of these I? So the answer is this one. Why? Because assuming that you have the analog signal, like speech signal, for example, having a spectrum like this. Normally we say that the information in the signal, a speech signal, is from 0 to 4 kilohertz. This is XCJ omega. But in practice, the natural signals, we can say that they never have a band-limited spectrum. They always, the spectrum always continues to the infinity. But the point is that with the first version, just C to D and D to C, as you saw in the reconstruction filter, you have infinite number of sigmas. Even if you say that it's not infinite, it's just from minus m to plus m. You're cutting from somewhere. But the point is that if you do not filter the signal, for example, from here to here, if you do not take just this part of the signal, and you allow the signal spectrum to go to the infinity, those repetitions, m times repetitions, in the final stage will give you like this. You have repetitions, so you have signals, periodic, then you have another one. I mean, this is, for example, the second period, this is the third period, but you know, the tail always goes to the infinity. But in this part, you have m times of the residuals. The first residual, for example, from this period is considerable. The next one may be much less. But you have m times something, even if it's epsilon. You know that. What is the answer? It's a value. But we don't know the value. It's ambiguous. So even if you have almost close to 0, but you have many times of those epsilons, you have something considerable here. Which means you're corrupting this part of the signal. All these parts of the signal, which are as an overlapping of the the following periods from the main one is actually corrupting part of the signal which is related to the higher frequencies. So the higher frequency portion of the spectrum of the signal in the end is corrupted. But in the second structure, what we try to do is we use a filter first. So we cut the information of the signal somewhere from here to here, and we have no information from this point forward. And if you make repetition of this, there would be no overlapping here. If the sampling frequency is enough, so you have no overlapping here. So much less amount of the higher frequencies would be corrupted. So even in general sense, it's much better to have a low-pass filter in the beginning than just using the continuous and A to D and D to A without a pre-filtering. This pre-filter is very important in every DSP structure, and it's called anti-aliasing filter. And we know that it's before we go through the A to D and D to A. So we are not in the sample domain. We are still in the analog domain. That's why this anti-aliasing filter is an analog filter. When I say analog filter, it means using the inductors and capacitors and resistors and so on. So in many cases, when you have a sound card or you have the capturing for the video, you have something in the beginning which is analog, and it's called anti-aliasing filter. If you don't use it, the quality of the signal in the end will be much less. So that was the intuition behind the anti-aliasing filter. But in general, you should know that the practical structure is a bit more complicated than the mathematical structure that we just read it in DSP theory. So we have anti-aliasing filter, which is called HAA, and it's analog. That's why you see HJ omega. It's in the CTFT domain and not in the DTFT. Then you have a sample and hold, and you do the A to D conversion. So you can just make a correspondence with the upper side. So you have samples here, then you do the discrete time system, whatever processing that you want to do in the computer. In the end, you pass the output to the D2A converter, and you have a filter in the end, which is corresponding to D2C converter. As I told you, the reconstruction filter. The reconstruction filter is here. That's what you have in reality, in the practice. Okay. So we talked about the anti-aliasing filter